like to know if ESP is real, so I could conduct an experiment. What I have are some very budget ESP cards, each of which contains one of 5 symbols, the classic ESP symbols, and we could conduct the following experiment. What I could do is I could shuffle up these cards and then one by one look at the symbol on the card and then try to project it into your mind. Kind of transcend time and space from when I'm actually recording this video to when you're watching it to see if we have some sort of unspoken mental connection. So if I look at that symbol, try to project it into your head, maybe you get it correct, maybe you don't get it correct. What we could do is repeat this experiment multiple times and see how many total guesses you get correct. So this is the third card that I've shown. Maybe you've gotten 1 correct, no correct, 2 correct, etc. After I've shown all 20 cards, if I were to repeat this again and again, how could I use this data to come up with a good guess for what P might be in this case, the probability of correctly identifying the card that's being displayed? If ESP was not a thing, well, probability would be 1 out of 5. There's a 20% chance that you would be guessing the correct symbol if the symbols are being presented just purely at random. If P was bigger than 1/5, well, that would be evidence for ESP. If P was less than 1/5, well, that would be evidence that some sort of inhibition process is happening where I'm actively blocking the correct symbol from your sight. And so if I did have a collection of data, let's say 60 different students participated in the experiment, I have a collection of numbers for the number of correct guesses out of those 20 different cards that the students have guessed. How can I come up with a good guess for what P is for using that sort of data? And so that is where we'd like to turn our attention to now. We've collected some data. We can propose a probability model like a beta distribution, a binomial distribution, for this ESP example, a normal distribution. How can we figure out the best flavor of that distribution that fits our data? So, for example, I might have the following histogram of data values from some data that I've collected. The data values range between 0 and 1, so the beta distribution would be a logical proposed choice for the probability distribution because that's a good model for anything constrained between 0 and 1. The question becomes, well, what 2 parameters, the alpha, the beta, the shape 1, shape 2 parameters, are going to be the best fit for the data itself? Now, FitDist, like a champ, has let us know what the best fitting parameters are, but you might have wondered, well, what's the process going on behind that? How does FitDist know what the right set of parameters are that's giving the best fit to the data? We know the beta distribution comes in a lot of different flavors here, a lot of different shapes. We can tweak those parameters at will. What's going to be the overall best shape that's going to reproduce the data that I've collected? And that's going to be the goal of estimation. We have a probability model in mind. We just don't know what flavor that probability model is the most appropriate. We don't know the parameter of that probability model that we should be using. So how do we do this process? How do we figure out the right probability model based on data that we've collected? Now, I've already thrown out one of those key terms that we want to keep in consideration with this discussion when talking about the parameter of the distribution. So a parameter is just some number that helps to define the shape of the distribution. The normal distribution has parameters mu, the peak, and sigma, the half width of that curve. The Poisson distribution has parameter lambda. The binomial distribution has parameters n, the number of trials, and p, the probability of success. And that is what I would like to estimate based on some data that I've collected. I want to know what flavor of binomial distribution is actually generating the number of correct guesses that people are coming up with to these ESP cards. So when I do this, when I've collected some data and I want to be data-driven and have that actually suggest the probability model, what I'm going to do is I'm going to measure something about the data to help with that guess. So whenever I measure something from a data set, the quantity that I've measured I'm going to refer to as a statistic. So any number that I calculate from the data is a statistic. The sample average, which I universally abbreviate with x bar, is a statistic because it's calculated from the sample values. The sample standard deviation, which is usually abbreviated with an S, is a statistic because it's calculated from the sample values themselves. The median of the sample, the max of the sample, etc. So we have parameters, which are values associated with probability distributions that dictate the shape of that distribution. And then we have statistics, quantities that I measure from sample values. Now, as we've seen, there's a lot of different symbols for the parameters of probability distributions, mu, sigma, lambda, etc. What we're going to do is just come up with a universal placeholder for the parameter of a probability distribution, and we're going to call that by the Greek letter theta. And so what we can say really is that the overall goal of the field of statistics is to try to come up with something that we can measure about the data that we've collected, some statistic that allows us a good glimpse as to what the actual value of the parameter of that probability distribution that's making our data. So in other words, what can we measure from the data? We'll give that a symbol theta-hat, an estimate of what theta is. That provides really good guess or really good insight as to what the parameter of that probability distribution is, theta. So how do we go from theta-hat, something that we've measured from the data, to theta, what's going to be the best choice of the statistic that we come up with, the best choice of our estimator? Well, there's a few ways to approach this problem. And in this unit, we're going to cover two main ways of coming up with good guesses for those parameters of probability distributions, the methods of moments estimator and the maximum likelihood estimator. And when we dive down a little bit deeper into the theory of estimation, we'll see that the maximum likelihood estimator is the superior way of doing estimation in general. But we want to approach both different ways so we can see that there's a variety of techniques that we can use to come up with reasonable guesses for what those parameters of these probability models that we like using might be. A unifying assumption behind all procedures for estimation is this assumption that we're going to be dealing with a random sample from the probability distribution. So what is a random sample? Well, number one, all the data values that we're collecting are coming from the same probability distribution that we're trying to come up with the best fit. And number two, each of the values that we're collecting are independent of one another, meaning that the values that we've collected in the past don't influence the values that we might collect in the future. Now, the way that we abbreviate this in statistics is to say that we have an i.i.d sample, identically and independently distributed, identical, meaning that it's all coming from the same data generating distribution, F, our PDF or PMF, and the second I being independent. Values in the past don't influence values in the future. There's no correlation between the values that I'm collecting when I go and collect data from the distribution. And so that's where the twiddle notation actually arises that you've seen before when we discussed hierarchical models. What we're going to say is that xi twiddle, i.i.d, a little bit above that, f. So essentially every single value of x that I collect, x1, the first value, x2, the second value, x3, this third value, so on and so forth, is all coming from the same data generating distribution with a PMF or PDF that we'll just denote by F, and all of the values that we're collecting are independent of one another. In other words, we have a random sample from our probability distribution. So given that we have a random sample from the PMF or the PDF that's generating our data, how do we go about measuring something from the data to come up with a reasonable estimate of what that theta parameter might be, the parameter that's controlling the shape of our proposed probability model? Well, one way to go about doing this is to use the methods of moments estimator. And I think from a philosophical point of view, this approach makes a lot of sense. So from the data, we can go and measure the sample average. And one thing we know about PMFs and PDFs, any probability distribution, is that we can come up with what the formula is for the expected value or the average value of that probability distribution. And so the methods of moments estimator says, well, why don't we just equate these two? We have an average of our sample, we have an average of our probability distribution. Let's choose the parameter so that those two averages match. The average of the PMF or PDF matches the average that we've calculated from our sample. And so this way, it kind of makes sense. We can very quickly come up with a reasonable guess for what the parameter of that distribution is just by taking our expression for the average of the PMF or PDF and equating it equal to x bar, our sample average, and then just doing a little bit of algebra, solving that equation for the value of our parameter. So, for example, if we were dealing with an exponential distribution, we have the following PDF, where lambda e to the minus lambda x is the data generating distribution. And if we go through the math to figure out, well, what's the formula for the expected value or average of this distribution, we find that the formula is just 1 over lambda. So the average value of this PDF is 1 over lambda. If we go and measure an average from the sample, x bar, the method de moment says, well, let's make the average of the data generating distribution equal to the average of the sample values. And so we get an equation, 1 over lambda equals to x bar. In other words, our good guess for what lambda is would be the reciprocal of the sample average. If we measured 1.75 from the sample values for their average, we would just take the reciprocal to come up with a reasonable guess of what lambda is. So to come up with the methods of moments estimate, here's the procedure that we can follow. So number one, what we're going to do is we're going to come up with a formula for what the expected value is of the probability distribution. So we'll take the integral of x times our formula for the PDF, if we're dealing with a continuous random quantity, or we'll take the sum of x times the probability of observing that value of x over all the possible values of x we might observe, to get our formula, which is going to depend on theta itself, the parameter of that probability distribution. We'll take that formula, set it equal to x bar, and then do a bit of algebra. We'll solve that equation for our unknown parameter. We'll put a little hat over theta to denote that it's going to be our estimated value of that parameter. And if our distribution happens to have more than one parameter that we need to estimate, if we have two parameters, well, we need two equations. Two equations, two unknowns, we'd be able to solve for both. And so methods of moment says, okay, well, we can also sit down and calculate the variance or the standard deviation of our probability distribution, come up with a formula for the variance, which will depend on the parameters of that probability model. We can measure the variance from the data that we've collected, and so we can just set those equal to. Let's have our probability distributions, variance and average, equal to the variance and average in our sample. So a few examples, well, we can look at the Poisson distribution. How can we come up with a reasonable guess for what the lambda parameter is of Poisson? Well, we can either go to Wikipedia to look up the formula for the expected value of the Poisson, or we can throw it into Wolfram Alpha to have it perform the sum. But what we would find is that our equation for the average value of the Poisson distribution is just lambda. So if we wanted to set the average of the probability distribution, lambda, equal to the average of the sample values that we've collected, x bar, our equation's pretty much done. We have that lambda equals to x bar, so we put a little hat over lambda to denote that our estimate for lambda in this case would just be the sample average from the data itself. Back to the exponential distribution example that we worked through, well, if I write down the formula for the PDF of the exponential and then go through the math to figure out the expression for the expected value or average of this PDF, I find that the average of the PDF is 1 over lambda. So what I do is I take that expression, I put the equal sign, and then I put an x bar. I'm setting the average of the probability distribution equal to the average of my sample values when I go collect them. And then I just solve that equation for lambda in this case. After a little bit of math, I find that lambda hat, my best guess for what lambda might be using this methods of moments estimator, is just the reciprocal of the sample average, whatever that turns out to be when I go and collect data. One more example, the Pareto distribution, which we've used a couple of times before, has the following PDF. Let's say that it's equal to alpha times 2 raised to the alpha over x to the alpha plus 1 for values of x that are bigger than 2. How could we come up with the methods of moments estimator for the Pareto distribution written this way? Well, step number 1 would be to come up with the equation that gives the expected value or average for the PDF. So we ask Wolfram Alpha to integrate x times our formula for the PDF over the range of possible values of x we might see from 2 to infinity. And we get the expression that the average value of the PDF is 2 alpha over alpha minus 1. So we take that expression, we put an equal sign, and we have x bar on the right-hand side. We're going to have the average of the PDF equal to the average of the sample values that we end up measuring, and then we solve this equation, in this case for alpha. We can get Wolfram alpha to do that algebra for us, or we can just do it by hand. In the end, though, we would find that alpha hat is going to be equal to x bar over x bar minus 2. So once we've gone and actually collected some data values, get the sample average, well, sample average divided by sample average minus 2 is going to be a reasonable guess of what alpha is. Now, in some cases, we're not actually going to be able to solve that equation. We're not going to be able to solve the methods of moments equation. So, for example, the logarithmic distribution, a PMF that we haven't discussed before, but it's been used to model brand abundances. So, how many different types of detergent do people buy when they go to the grocery store? How many different brands of apples? 1, 2, 3, 4, etc. We have the following equation that gives us the PMF. So if I want to figure out the methods of moments estimator for the parameter of this probability distribution, it looks like the parameter is named P in this case, I need to go and figure out the expression for the expected value. So I can go ask Wolfram alpha to take the sum of x times my formula for the PMF over all the possible values of x that I can see from 1 up to infinity, and I get a relatively complicated looking expression for the average of the PMF. Now, the methods of moments estimator says, okay, take that expression, put an equal sign, then x bar on the right-hand side, and then solve for p. But this is going to be one of those equations that I'm actually literally not going to be able to solve. I can't come up with a closed form expression for the solution to p because none such exists. This happens to be a transcendental equation because it transcends our ability to solve it in the form p equals to ... some simple expression involving x bar that we can use. Wolfram alpha kind of tells us that this is the case. If we actually go and ask Wolfram alpha to solve this equation, we get a standard computation time exceeded, indicating that we either need to upgrade to Pro, kind of trying to make us pay for the service. But really what it's letting us know is that, hey, this sort of equation doesn't really have an easy to write down solution. I can't go p equals to some function of x, so I can plug in that value of x to get the methods of moments estimator. It's something that needs to be solved actually on a case-by-case basis. So unlike the previous examples, I don't have a nice simple rule for what I can do to the sample average to get my methods of moments estimator. I actually have to collect data first, get a value of x bar, and then I can actually get the methods of moments estimator based on that. So how could I do that? Well, let's imagine I go collect some data and I do find that the average value is 2.2. So in this case, I can ask Wolfram alpha to solve the equation. My expression for the average value of the PMF equals to 2.2, the observed value of that sample average. And Wolfram alpha can do that with very little issue. Now, like a lot of things, Wolfram alpha is really designed for mathematicians. It's a little bit too mathy for us. It comes up with a really weird looking expression for what that solution for p hat is. But we can always select the approximate form to come up with a decimal approximation for that answer. And so once we do that, we find that based on my sample average of 2.2, a reasonable guess for p, my p hat from the methods of moments estimator, is going to be about 0.756. Now, I was mentioning that if the probability distribution has two parameters, well, we're going to have two equations so that we can solve for those two unknowns. The equation that equates the average value of the PDF or PMF to the sample average is one of them. That second equation is going to be taking the variance or standard deviation of the PMF or PDF and setting that equal to the sample variance or the standard deviation. So two equations, two unknowns, we'd be able to solve for both parameters. So take, for example, the gamma distribution, which has the following equation for the PDF. There's two parameters that we would need to estimate from the data, the A and the S parameter. So how could we do this? Well, we could go and actually, calculate the mean and the variance of this distribution on our own, or we could take a quick trip over to Wikipedia and say, hey, what are these two formulas? And in this case, these two formulas are relatively simple. The formula for the average of the PDF is just the a times s parameters, and the formula for the variance of the PDF is just a times s squared. So to get the methods of moments estimators, I need to set up our two equations. I'm going to take my formula for the expected value, a times s, and then set that equal to x bar, the sample average that I'll eventually measure. And then I'll take the equation for the variance of the PDF, a times s squared, and I'm going to set that equal to the sample variance. I'll just denote that by capital V. Two equations, two unknowns. I can either solve that set of simultaneous equations on my own, or I can also ask Wolfram Alpha to solve that set of equations. Now, when I do ask Wolfram Alpha to do this, Wolfram Alpha very often will output more than one solution, so I just have to go through each of the proposed solutions and pick out the one that makes the most sense. In this case, I guess the solution is to take a equal to 0, x equal to 0, and v equal to 0. That doesn't make any sense because x is my abbreviation for x bar in that equation. V is my abbreviation for the sample variance. Those aren't going to be equal to 0, so that can't be a solution. Really, the only solution that makes sense here is to take my a hat to be x squared over v in my notation. X is my abbreviation for x bar, so the square of the sample average divided by the sample variance. And then my best guess for the s parameter, my s hat, would be the sample variance divided by the sample average. Now, the beta distribution, which we started out with for this unit, has actually pretty complicated formulas for the average value and the variance of the distribution. They're very complex functions of both the alpha and the beta parameters. So if I did want to solve for the methods of moments estimators, that would take some pretty hardcore algebra skills. Luckily, Wolfram Alpha can solve this set of simultaneous equations for us. We essentially take our expression for the average value of the PDF, set that equal to x bar. I'll abbreviate that in Wolfram Alpha just with a capital X. We'll take our expression for the variance of the beta distribution, set that equal to just capital V, our sample variance, and ask Wolfram Alpha to solve both those equations simultaneously. We'll have to go and hunt for the one that makes the most sense, and the one that makes the most sense gives the pretty complicated expressions of what I need to do with the sample average and variance to get my alpha hat and my beta hat here, my methods of moments estimators. But the nice thing is that they exist. Regardless of whatever sample values I end up collecting, I can get that sample average, I can get the sample variance, and I can just throw them into that equation and come up with reasonable guesses for what the alpha, the beta parameters of that beta distribution might be. Can I get a good glimpse as to what the shape of that beta needs to be in order to reproduce my data fairly well?